Hello, and welcome to a chemistry lesson with Science Mom and Math Dad. Special welcome to you if you're watching the replay, and a very warm welcome to Derek Michael, who has a birthday today. Happy birthday, Derek Michael.
Do you know how old?
I forgot.
Didn't write it down either. So congratulations, Derek. That's exciting.
Happy birthday to Mary Catherine from Maryland, to Ethan from Minnesota, Lindsay from California, Reem from Canada, Nella from Michigan, Amanda and Margaret, to Rachel watching from Nevada, Grace in South Carolina, Abby from Virginia, and Vivian and Colin from California, and Lily watching in Ottawa.
I'm seeing Ryan from Ottawa, Dexter and Garrett from California, Grace from South Carolina. Got a great crew today. I think we're ready to go. So we have a slow chat on, right, Science Mom?
We do. And a quick important note. First, I want to say 2020 has been a stressful year for pretty much everybody. And it's stressful because there's a lot of uncertainty. And in the United States right now, we have a political election. There's a lot of uncertainty. Again, fairly stressful. So if there is anything political in the chat, whoever makes the political comment will actually be blocked. That means to be able to participate in the chat again, you'll have to email me and get my permission, which cannot happen until tomorrow. So no political commentary in the chat allowed.
Yeah, so stay on topic because we have some good science to discuss.
And we have a really interesting question today. The question is, why can't you eat books?
I know the answer. It's because they don't taste very good.
Well, true. What's the difference between edible and eatable? There are certain things that you could eat, but would you get any nutrition from them? Would they be good for you? We cannot eat books. If you eat a book, it's not going to be good for you. It's not going to give your body energy, but there are animals who can.
Really?
Yes.
Like a beaver could eat a book, maybe?
Well, books are made from wood. And beavers, although they do chew up wood, beavers don't really eat wood as their primary source of food, but termites do. Termites eat wood, and there are other animals like cows and horses that eat grass. And grass is made of a really similar material as these books. So our question today is why? And as you may have guessed, the answer has to do with chemistry.
Oh, okay. And they're asking what that book was you were holding up.
This book is a kid's guide to a periodic table, which goes along rather nicely with our class. So that's why I grabbed it, because the periodic table is something we've talked about a lot in the last few weeks.
Gotcha.
But would you like to eat this, Math Dad?
You know, I already ate breakfast. I'm probably good. Thank you.
No.
Although Team Feed Math Dad in the chat is probably rooting for it.
To understand why we don't eat books, let's review what we learned last time about sugars.
Oh, I remember. Sugars were made up of two submolecules.
So the sweet sugar that you get from your cupboard, called sucrose, is made up of glucose and fructose. Those two rings of carbon stuck together make sucrose. Now let's come to this other view and look at some other sugar options. So here is sucrose. Whoops. The sweet sugar that you eat is actually made of two molecules stuck together.
Glucose?
Glucose.
Glucose is green. Okay.
Yep.
Green
6
for
carbons and fructose.
Fructose is the orange. Okay.
But if I take glucose and then I attach it to another glucose and another and another and another and another, and I make a big long chain of glucose, guess what I have?
Well, you said glucose didn't taste as good, so I'm guessing this is not as tasty.
It's not going to be sweet. But it is going to be a food that we can eat. It's a big long chain of glucose. What do you think it is? I'll give you a hint.
Delicious? Nutritious?
It is nutritious. And you ate some this morning for breakfast. It's
shredded wheat.
Starch.
Starch. That's what I was going to say.
Yes. So if you eat wheat or if you eat a potato, you are eating quite a bit of this. This is starch, a big long chain of glucose. And when it goes into your body, you have special things in your body, special proteins called enzymes, and they say, hi, yeah. And they break it up so that then you can digest the starch and turn it into sugar and use it for energy.
Because glucose was what was giving us the energy.
Yes.
Remember, we learned that last time.
That's right.
Okay, so you said there were like little ninjas in our body that were karate chopping all these. What was that again?
So the enzyme, the name of that enzyme is actually alpha amylase. Let's go back to our big view here.
Okay, an enzyme.
An enzyme. Enzymes are like little factories that can make a chemical reaction happen. And the special enzyme alpha amylase is in your body. It's in your saliva, actually, just a little bit in your saliva, but also in your digestive system. whenever it sees starch like this, it says, ha, and it chops it in half. And you can actually do this with an experiment. If you put a little piece of cooked potato or a little piece of a cracker in your mouth and chew it up and make sure there's lots of saliva with it, hold it on your tongue for just a few seconds, and you can start to taste that it tastes a little bit sweeter. Glucose is not super sweet. It's not as sweet as fructose, but it is sweet. Just a little bit. Sweeter than starch tastes.
Okay.
Isn't that awesome?
That is really cool. So enzymes are little ninjas that are making these reactions happen.
Making reactions happen. Yes, enzymes make reactions happen. And so this is how we eat starch. Now here is the awesome, mind-blowing part. Let's go back to our table, and I'm going to show you what wood is made out of. You ready for this, Math Dad? You're gonna be amazed.
Okay.
So here I have a whole bunch of glucose.
Wood is made of glucose.
It is, but these glucose molecules, instead of being hooked up like this, they're flipped. So this is
every other one is
cellulose. This is wood, and then here is starch, like in a potato. Whoops. And
so it's all glucose no matter what?
It's all glucose no matter what. They're both all glucose. But in this one, everything is facing the same direction. And I can turn it over this way.
Just the orientation is changing.
Yeah, and this one, every other one is upside down.
So just like this one we called starch because it was all glucose facing the same direction.
This one is cellulose.
Cellulose, and that's all glucose, but it's alternating in its orientation.
And guess what? The little ninja enzymes that we have in our body, when they see this bond, they go, hi-ya, and they try to break it, and they can't. And so we cannot digest cellulose.
Wait. But it's the same, it's just glucose.
Switched around. And the way that that chemical bond is between those two carbons, linking between the carbon and oxygen, linking them, we can't break it if it's like this.
Somehow the enzyme is able to break these apart.
But not
these. So like this is a stronger bond, or
it's a different bond.
And the enzyme just has a particular set of skills.
Yes, enzymes are super specific. They can only make certain reactions happen. Isn't that crazy?
That is crazy because it's just the same molecule over and over again.
Yeah, same molecule, but different arrangement, just arranged differently. Let's go back to a big view, and I want to tell you something cool about termites and about horses.
Now, is that what they call a polymer? Yes.
So here are our two cool words of the day: monomer and polymer. If I have just one piece of glucose, that's a monomer.
Mono means one. Singular. Okay.
And if I attach a bunch of them together, now I have a polymer. Poly means many.
Like polygon.
Like polygon.
Like things like triangles or rectangles or pentagons, hexagons. Those are examples of polygons, which means they have many sides figure. But a polymer, I don't know what a mer is, but it's a many mers. It's many units.
Many units. So monomer means one unit. Polymer means many units. So sawdust is made of a long polymer of glucose. But if we eat sawdust, it's not going to give us energy. And it's not going to be good for our stomach and our digestive system because we can't digest it.
It sounds terrible, but have you ever tried?
Have I ever tried eating sawdust? No. But back in the 1700s, there used to be millers, people who grind wheat into flour. They would sometimes add sawdust to their flour because it was cheaper. And then there were certain laws that were passed that said no sawdust in flour. That's not allowed.
Oh man, that's funny. Kind of cruel, but
not very
I'm not even surprised. So now that you mention it, of course somebody was going to think of that.
But if you're a termite, sawdust is very tasty, and that's all because of bacteria. I thought that's not what you thought I was going to say, right?
I thought they were just hungry.
No. But they have special bacteria in their stomachs, and the special bacteria in their stomachs, when they see this bond, they go, hi-ya, and they're able to break it and break it again.
They have stronger ninjas?
They have an enzyme that can break that bond. And this is why horses have 4 stomachs. Horses and cows, actually, I think horses have 3 stomachs, but all herbivores, animals that eat grass, they either have a very large stomach that's very specialized, or they have more than one stomach.
Because of termites?
Because they need special bacteria to be able to digest cellulose, to be able to digest the grass. They need special bacteria in there, and they can only do that if they provide a nice big home for those bacteria.
So wait. So this in their stomach full of bacteria that happen to have this enzyme that can break apart the cellulose?
Break the cellulose apart so that then it turns into glucose.
And then it's just as good as if it had been a starch.
Exactly.
Whoa.
Pretty amazing, right? Now, here's kind of a crazy thought. Only bacteria can make this enzyme. They're the only ones that can. But if you had this enzyme, let's say like in a pill, it would be like a super starvation pill, because then if you had this pill and you ate it, then you'd be like, oh, that tree, I can eat that tree. Those leaves, I can eat those leaves, because most plants are made out of cellulose. Isn't that kind of a crazy thought?
Oh, wow. Wait. So if we had this magic enzyme that the bacteria has, then we could just eat it as a pill, and then we could eat a book?
We could eat grass and we could eat a book, and we would get energy from it. But I have to point out, and this is really important, sometimes wood and books and other plant material, sometimes there's more in there than cellulose.
Oh, yeah.
And there are other things that you might not want to eat.
Oh, my goodness. Well, that's kind of crazy to think of, though.
Let's turn to the notes real fast, because before we are going to talk a little bit more about polymers and monomers. But first, Math Dad, I want to challenge you to a secret code chemistry drawing contest.
Oh, kind of getting on with what we had done last time?
Yes. Okay. And if you have pen and paper, I hope you will pull out some pen and paper and join us and see if you can draw what we are going to draw.
Okay. So
ready, Math Dad?
How's this challenge going to work?
Okay, so my first one I'm going to give you is pretty easy. I'm going to give you a bit of a review. I'm going to draw this right here. A line up and then a line down. And if you remember, this is the chemist's secret code for drawing carbon. Because if we're drawing carbon and hydrogens, there's so many carbons and hydrogens in the molecules we care about that we want to draw that we get tired of drawing all those carbons and hydrogens. So can you remember, Math Dad? I'm just going to do an equal sign here. Can you show us what that is?
I think we did this one last time.
We did.
Do a volcano out of it or something.
Yep. I'm starting easy on you.
Okay. All right. So we know that there are 1, 2, 3 endpoints of line segments. So I can just put a carbon at each of them.
And Aaron Walker already knows what it is. I put it in there.
Okay. And then each carbon has to have 4 bonds.
That's right.
So this one already has 1. We need 3 more. This one needs 2 more, and this one needs 3 more. So I just have to toss H's on there, because by default it's always an H that we attach. Oh,
you did 3 up there, Math Dad. Erase one of them.
I did. Let me dispose of the evidence. I didn't see anything.
Good save.
Okay, and then this one we get 3 of. Okay, so now every carbon has 4 bonds, and every hydrogen just wants 1 bond.
That's right. Hydrogen just wants 1 bond. Okay. And a big shout out to Diamond Star and several others in the chat that have said this is propane. You're exactly right.
Oh, they even remembered the name.
Yeah.
Okay, that is impressive.
Now,
I didn't remember that.
We have 3 carbons, so the name of this, the chemical formula, would be C3. And then how many H's do we have? How many hydrogens?
Looks like 8.
Yep. So that is propane.
So C3H8. But wait a minute. If you know this, does that mean that you can redraw it this way or get the secret code?
A lot of the time, yes. But sometimes you have 2 molecules that will have the same chemical formula, but they're different.
Oh, so actually drawing out the shape is going to give us a better understanding than just writing.
And cellulose and starch is a really good example of this, because here I just made a really simple drawing of our cellulose, and I didn't even draw the hydrogens or all the carbons and oxygens. I just put little smiley faces to make them kind of cute. So then you could tell in starch, they're all facing the same direction. Mm-hmm. But in cellulose, every other one is upside down. Do they have the same number of carbons? Yep.
Yeah.
Same number of oxygens? Yep. But this link...
The formula is going to be the same then.
Yeah, but this link between the bonds is so different. That makes a huge difference for us. When we eat starch, our little enzymes, which Math Dad nicknamed little ninjas, they can break this bond really easily, and then we're able to get the glucose. But when we eat cellulose, we cannot break that bond. They try and they're like, oh, it's too hard. We don't have the special bacteria to break it.
Okay, I need some clarity. So if I go back to page 49 in the book, glucose looks like this. It was big and kind of complicated. So you're saying that glucose that was actually bigger and complicated, and which would combine with fructose to make sucrose, but that one, you're saying you redrew it just as a cute little molecule.
A cute little cartoon, yes.
And then, okay, now that makes sense to me. So there's something a little more complicated than what is drawn here, but that's the basic idea.
Now, Kieran says, why would anyone want to eat trees?
Nice one.
Why would anyone want to eat cellulose is my question. Because if you look at that and you say, well, I can't digest it, you might think, well, I should never eat cellulose. But...
Well, okay, so that's a good question about whether one could eat cellulose. But before we get to that, Science Mom, I didn't give my challenge.
Oh.
You guys see what she was trying to do there? She was trying to escape without doing her challenge. So I'm going to dispose of this, and I'm going to make up a problem. We'll see if Science Mom can do it. So I am going to go make a hexagon.
Ooh.
And I'm going to throw in a double bond here.
You should add some other elements besides carbon, just for fun.
Double bond here.
Oh.
Don't worry.
It's getting interesting.
Okay, I'm going to draw a pentagon down here, but I'm going to throw in an O at the bottom.
Oh, okay.
And, okay, so let's see if you can figure out my super secret chemist code answer to this.
All right, I'm going to draw it. Did you look this up in advance? Is this a real molecule, or did you just make it up?
Oh, I totally just made it up.
Okay. Well, we have 2 carbons there in that middle part, and then another carbon here, and then I need a double bond between these carbons, a single bond, a carbon, and another double bond. And there is my, let's check and make sure, because this is a hexagon. Is this a hexagon as well? It is.
Good. Okay, I'm with you so far.
Okay, and then I'm going to make my pentagon with carbons, and here I have a bond to an oxygen instead.
Okay.
Because this and this goes to the oxygen, and that's this part here. Now I just need to make sure the oxygen wants 2 bonds, so my oxygen is happy, but my hydrogens I'm going to draw in with blue, and I just need to make sure that each carbon has 4 bonds. So there we go, 4 bonds for that carbon. It's happy.
Okay.
This one, 1, 2, 3, it only needs 1 more hydrogen, and it's got 4.
Agreed.
Same here, 1, 2, 3, 4, 1, 2, 3, 4. So lots of carbons that just need 1 more hydrogen, and 1 more hydrogen here, and 1, 2, 3, 4. Ta-da! I drew it, Math Dad. I deciphered your molecule.
Wait. What about the? Looks like you drew an extra line.
Oh, sorry.
I was fixing that.
Good job.
Wait. What happened to the oxygen? Does it need anything?
2 bonds, and it has 2 bonds. Oxygen likes 2 bonds, hydrogen likes 1 bond, and carbon likes 4.
Okay. All right. You got lucky that time, Science Mom. Next time I'll stump you.
You can try. You can try, Math Dad. Now, I want to show you a couple other monomers and polymers, because this is really cool. A monomer can be put together to make a polymer, and you can do it with anything. So if you have a pearl necklace, that is a polymer of pearls.
Because it's just
lots of units of
many
pearls.
Units of. Oh, wow.
Now, let's go to our tabletop view. I just want to show real fast. We said that if you have sugars and you put a bunch of sugars together, you can get a polymer of starch. And here's our starch molecule. Or if you flip every other one over, you can get a polymer of cellulose. And this is the main ingredient in wood.
Okay.
But we have so many other polymers, you guys. One of my favorites is protein. So this just is a little circle to represent an amino acid, and it's something that contains nitrogen. That's what our N's are for.
Oh, I thought an N for amino acid, and I was going to tease you about your spelling.
No. So amino acids, hook them together, you get protein. Nucleic acids, put them together, you get DNA. Polymers are all around us, but the ones we're talking about today are starch and cellulose.
Okay, I still don't know what a protein is, other than that you can link stuff together. Are you going to talk about that more today or some other time?
I have brought a protein guest. Would you like to meet my protein guest that I brought today?
Yes.
All right. We have...
What is she talking about, guys? Should I be scared?
No, you should not be scared.
All right.
Unless you're scared of a little tiny mess, because we might have just a little bit of a mess.
Wait a minute. I do know what you were setting up earlier. Let me jump back. Okay, so this
is a reaction that we have done before, and it is elephant toothpaste, one of my favorite reactions. So in these bottles here, we have hydrogen peroxide. That is 2 oxygens and 2 hydrogens. And there is an enzyme, a protein, that can split that oxygen and hydrogen apart to make oxygen gas and water.
What else is in this?
A little bit of soap. That's it. Hydrogen peroxide and a little bit of soap.
Did you have to mix it up, or did you just pour it in?
Oh, are you noticing that my soap is settled to the bottom?
Yeah, that's what I was noticing. There's a little bit of a green color there, and I was concerned that somehow that might affect our experiment, because I want maximum toothpaste in our elephant toothpaste.
Now we're ready. So we have hydrogen peroxide and soap, and this is 3% hydrogen peroxide, so it's pretty safe. And here we have yeast, and the yeast is actually a tiny little fungus, and it has a protein inside it, a protein that is an enzyme, and that means it can make a chemical reaction happen. And if you guys remember this, we did this about a month ago. It's pretty fun to see this happen, but this time I'm doing it as an experiment because we have twice as much hydrogen peroxide in this container than in this one.
Okay.
So I want you to tell someone that you're watching with, tell them what your prediction is, because this little enzyme here, it has to cut all those molecules and break them in apart to release the oxygen gas. Is it going to take twice as long to do this one?
Or will you get twice as many bubbles? Is that what you're asking?
Yeah. Or will they happen about the same time?
Oh, so will one of them happen faster than the other?
Yeah. What do you think?
I see more foam. I don't know.
We're going to put
because it's the same concentration, though. That's an important detail, right?
Yeah, same concentration,
it's just
same temperature.
The amount of liquid happens to be bigger in one bottle than the other. So surely the one with the bigger bottle would have more potential to foam more,
but
right?
If the enzyme's job is to break it apart, and it's the same amount of enzyme, do you think that it'll take it longer to do the big bottle?
A little mix more, though.
You ready to find out?
Yeah, I'm totally ready. Okay.
All right, here we go, Math Dad. It looks like we're maybe not adding the same amount, but that's just because this container is bigger.
But you measured it?
I measured it, and they're the same.
Okay.
Are you ready?
We don't need safety gear for this one, right?
You know what? We should always wear safety goggles just because it's fun. Safety goggles on. This one, we're not doing anything dangerous. There's going to be no pressure, but safety goggles are always a good idea.
All right. Well, now it's official.
Yes. 3, 2, 1.
Okay.
And I added blue and yellow food coloring up at the top.
Okay. I'm liking this color scheme.
And even though we have the same amount of enzyme in both one, I think our one that has a full cup is going to erupt first.
It's definitely going a little bit faster.
Ooh.
Interesting. Look at that mess it's making. Thank goodness for that tray.
There we go. Push it forward so you guys can see.
Oh, now the other one has reached the top. All right.
They're coming out pretty quickly. Now, here's my favorite part, Math Dad. We get to be artists. You ready? Grab some food coloring, whatever colors you want. And we are going to...
My wife doesn't let me play with food coloring usually. But that's not true.
We are going to add little droplets, and then we're going to see what kind of patterns they make in the foam as it comes down. And now I'm gonna pull it back just a little bit more so you can see the foam.
Okay. This is cool. Okay, so what you were saying that this relates to eating books. How? Remind me.
So this enzyme catalase is a really common enzyme that we have in our bodies too. And this is why if you put hydrogen peroxide on a cut, wherever your skin is broken, you will start to see bubbles forming because the enzyme catalase is inside you too. It's not only in yeast, it's also in us. Most living things have this enzyme in them. And the main reason that I wanted to talk about enzymes and catalase is because we didn't really have a full day for proteins, and proteins are super important. So I just wanted to make sure that we mentioned this. And then also
the catalase is an example of a protein.
It is. It's a protein that can make a reaction happen. And the whole reason why we can't eat books is because we don't have the protein that can break that bond. So there's a chemical reaction that has to happen for you to be able to break cellulose apart, and we don't have that enzyme. So that's why we can't eat books.
Okay, that's pretty cool. Now, as to which one's actually going faster, I think the one that had more hydrogen peroxide, is growing faster still.
It is going faster, but you know what's amazing about this enzyme, Math Dad?
What?
It can, guess how many reactions it can do per second?
I don't know, 10?
It's thousands.
Oh,
it can do thousands of reactions per second. So it doesn't matter how much hydrogen peroxide you give it, it can just
powers through.
Yeah, it can do that reaction.
It's consistent the way it just keeps going until it must run out of.
Are you feeling nervous about the state of foam, Math Dad?
It's starting to get up to the edge. I'm ready to run and grab a towel.
I tested this in advance, and it should stop just right as it gets full so that it won't make a mess, but it made Math Dad nervous, which I think is perfect.
Living on the edge, Science Mom.
That's right.
Always living on the edge.
Now, let's go back to our main view. We will come back and show these again at the end, but we have a Chem Mystery that I wanted to share. And then we also have a couple questions, and I have a special shout out for people who have completed our periodic table challenge.
Well, I think we haven't gone through all the notes yet either, or at least I wanted to make sure that we talked about all of that. So
okay.
Plenty more yet to come.
So we want to give a special shout out to Camden.
Oh,
Yay!
Nice job, Camden.
Who completed all of the periodic table cards for the whole entire periodic table. And Reem in Canada and Adeline. Bravo, you guys. Good job.
Yeah, congratulations. That is super exciting to see. And that was a lot of work that you put into that. So kudos to you. You deserve some recognition.
We will do our Chem Mystery now and our questions, and then we're going to kind of come back to the questions. So if you have questions that didn't get answered, put them in the chat. Our moderators will send them to us, and we'll go back to the notes real quick. So the item pool link is the same as always.
Yep. All right.
And our Chem Mystery,
this one right here,
is right there.
Is this one going to stump them?
I think this one's a bit easier.
Okay.
But we'll find out.
Sculptures from this metal won't corrode. They'll just turn green. And this hygienic metal keeps our water pipes clean.
And if you're watching the replay, just take a minute to think about it and see if you can guess out loud before Math Dad reveals what the answer is. So a metal that turns green.
I'm not sure if I know what it. Oh, wait. I know. I think I know what it is. I think I know the answer.
Think you know the answer? Do you want to hazard a guess, or are you trying to wait for the chat to give you a hint?
Aaron in the chat agrees with me, so I'm more confident now.
What is it?
It's copper.
That is correct.
We saw that copper was starting to turn green a little bit when we were doing our lemon batteries or potato batteries, right?
Yeah, good job, Kari and Kristen and Tatiana and Kai. So copper is correct.
So we've seen that in like old pennies.
Mm-hmm.
They will sometimes turn green. So
and
is it getting dirty,
and
or is it actually
famous statue? The Statue of Liberty is green because it's made out of copper.
No
and
way.
Old pennies get green because they're made out of copper. They oxidize. The copper reacts with oxygen.
But if you just went and scrubbed it, would that?
You could. If someone was really ambitious, and I want to give a shout out to Era on this excellent element card.
Good job.
If someone was really ambitious and wanted to scrub the entire Statue of Liberty, they could make it look.
It would wipe away the green. Like is the green still part of the metal?
It is.
Is that just like a residue that's left on?
It's part of the outside layer. There's actually a chemical reaction that's happened between copper and oxygen, so it's hard to get off. You can't just like wipe it off. You'd have to use some chemicals and tarnish and scrub, but it would be possible.
Nice.
But I think copper looks really pretty when it's oxidized, so I hope nobody cleans the Statue of Liberty because it looks better green, bluish green, than it does copper.
It does have some nice beauty to it. So, but it would have been fascinating to see color pictures of the original before it changed color. Yeah, they didn't have color photos back then. So.
Nope. Huh. All right. Open up item pool, and we are ready now to start our quiz.
No, we're not.
No, we're not.
No, we're not. Just a second. So I will get us there, but I wanted us to.
Matt Dad was telling me this morning, he said, you go too fast when you get excited. And this is definitely a topic I'm excited about. So.
Okay. So I just wanted to make sure we understood everything on this slide. So You can't eat wood because it's made of cellulose. And the reason that you can't eat the cellulose...
you could eat it, but it wouldn't give you energy. It would just pass through and go out the other end.
So there's no reason to do it.
Yeah.
So we don't like to eat cellulose.
So the ancient times, the millers that used to put sawdust into flour and then would get in trouble for it, it didn't make people sick. People could eat their flour that had sawdust in it. They just didn't get as much energy from it.
So we could eat it right now. But in general, we don't want cellulose in our diet. So
we call it fiber. And you do want a certain amount of cellulose in your diet, and you get it from plants and vegetables and fruits, but we call it fiber. And it's actually a good thing. Like when you eat celery or when you eat whole grains and you get fiber in your diet, it helps to get rid of cholesterol. And it's...
So I'm getting mixed messages here now. So you do want fiber because you can't digest it, or what?
But you don't want too much of it.
Wait, why do you want it again?
Having fiber in your diet helps your digestive system to work better, and it's the only way your body can get rid of too much cholesterol. If you have too much cholesterol, then it attaches it to the fiber, and that's how you get rid of too much cholesterol.
Okay,
so this is kind of a nutrition lesson tangent.
But no, let's figure this out now. So celery, you said, has lots of
cellulose,
lots of cellulose. Somehow fiber sounded more delicious than cellulose. I don't know why.
Same thing.
Okay, same thing. And if I were to eat it,
you don't get a lot of energy from it, but having fiber in your diet is good. But it's all about the amount.
So I chew it up, it goes down, and then
out the other end.
It's going to go out the other end after getting mushed up and stuff. It doesn't get absorbed. It doesn't. I can't eat the glucose or absorb it. Whatever one does to glucose to get the energy from it. Okay. Now,
if you only ate celery, you would be a very sad human being because you would not be getting any energy. You'd be starving to death even though your stomach was full. But if you don't have any fiber in your diet at all, you are also a very sad human being who has a hard time going to the bathroom and maybe has cholesterol levels that are too high. So it's all about balance, right? We can't digest cellulose, but we still like to have some of it in our diet, just not sawdust.
So it might be a good thing that we can't actually break it down, that we don't have that particular enzyme that only the bacteria have. Okay, now can humans just take the cow bacteria and put it in their stomachs and then they can...
No, you have different bacteria in your stomachs, and you don't have 4 stomachs. So that the cow has a very specialized, different bacteria in different stomachs system, and lots of space for all those bacteria.
Oh, so the whole production system going.
And then it eats the grass, and then it regurgitates the grass and chews it again, and then swallows it again, and it's a whole big system.
But if you gave cows antibiotics and it killed all that bacteria,
that would be a very sad cow. The cow would not be able to digest its food.
And
termites
so does it just keep getting hungrier and hungrier, even if with a full stomach? There probably are little tiny sugars in the grass that it can digest, but yeah, for the most part, it could starve. Same thing with the termite. Termites and cows, they need bacteria to be able to eat. Wow.
And we digest our food better with bacteria too. That's why things like yogurt and probiotics you'll see in the grocery store, because we figured out wow, we do this better if we have bacteria.
Bacteria are kind of getting a bad rap sometimes.
Some bacteria are good, some bacteria are bad when it comes to us and which bacteria we want around.
All right. I get it. This is making a little bit more sense.
All right, let's go to item pool now, Math Dad.
Science mom and her rush to get through these. Okay, so that was one page of notes, but I just wanted to at least look at these other pages because we will get there. All right, so the challenge. All right, you had this whole other page of notes. So you were explaining here.
This is what we just talked about. Yeah, so rhinoceroses, goats, cows, horses, any animal that eats grass is only able to digest grass because of bacteria that they have in their stomach and the special relationship they have with their bacteria.
Okay, so it's that simple. Basically, if it's an herbivore, for the most part, it's got to have this bacteria.
Yeah, because the bacteria are the only organisms, the only ones that are able to, cut that bond between cellulose.
Okay, no, that's...
And then that's just a little thing about why fiber is important. We still want fiber even though we can't digest it.
Okay.
All right, now we're ready for item pool.
I can't delay any longer?
Nope, you can't put it off any longer. Math Dad, they're going to win this time. I know you're trying to avoid it, but
we'll see how that goes. I am not convinced yet. All right. So we are going to go live here. Our first question of the day is, what is the name of a long chain of identical units? Is it a colander, a polymer, a monomer, or a polygon?
I think you should be able to make that into a song, Math Dad. That sounds pretty nice. Go.
Colander, polymer, monomer, polygon. Colander, polymer, monomer, polygon. Go. Yeah.
Which one is it?
Oh my goodness.
Which one is the name for when you have a really long chain of units that are the same? So
colander, polymer, monomer, polygon. Colander, polymer, monomer, polygon. Oh,
that's like a tongue twister.
Oh. Yeah.
Colander, polymer, monomer, polygon, polymer, colander, monomer, polygon.
Okay, 10 times fast. Go.
That's pretty challenging.
Waiting for them at home to trip over their tongues. They're like, come on, Math, Dad, I can do better than that. No, you can't. See?
Oh, I bet they can. Colander, polymer, monomer, polygon.
Yeah, it is easier when you're reading straight from there, but yeah, trying to remember that. That was hard. All right, everything's getting some votes.
But one of them has more votes than all of the others, and I'm betting that it is the correct answer, which is...
Oh, somebody's got the link in there. All right, so the actual answer is...
Polymer.
Polymer. So remember, poly means many, and mer meant units.
And so
many units.
A long string of glucose, that is starch, or if you flip every other one the other way, it's cellulose, which is like the big building block molecule of all plants.
Like, so when you look at like celery, it kind of looks like it's in strands, or break it apart. Is that related to this at all, or is that too big of a structure? And
yeah, that's a bigger structure.
Okay.
And protein is a big long polymer of amino acids. So many things are polymers.
Question number 2. Starch and cellulose are both polymers made of, is it glucose, fructose, sucrose, or lactose?
They totally know this one too, Math Dad.
Oh, okay. Well, sometimes you got to give them easier ones so that then you can stump them later. Okay. All right, but yeah, I'm really not fooling too many. Maybe they're picking the wrong answer.
I don't think so.
52 votes for that one. I don't know. So Angry NPC asks, how does one know the density of a polymer without measuring it?
That question maybe is a little bit beyond what we have time to get into.
So maybe, if you knew you only had one type of polymer.
Yeah, like how do you know how long the chains are? There's several different ways that you can get that information, but yeah, I don't think we quite had the time to go into that.
But for the most part, it's something that has been measured many times. So if it's a known result, it's because of a lot of measurements.
And one of the big differences between different types of starch, like potato starch is different than tapioca starch, is different from wheat starch, has to do with how long those chains are and if they branch, if there are any branches, because some starches do have occasional branches. All right, let's finish and reveal.
All right. And the answer was glucose.
Good job.
So glucose, we said, is the one that's given us our energy. So we like that one.
Glucose is like the currency of our body. And that's what you have in your blood right now. If you measure your blood sugar, glucose is what is in there.
All right, this is the one. Question 3. An enzyme is a state of matter, a carbohydrate that stores energy, a starch that changes color, or a protein that makes an action happen.
Ooh.
So they're...
This one is a little tricky because when we were talking about this one, we used 2 different words when we were talking about it.
We did.
Yeah, but I won't give hints. I'll wait until...
Lots of words showing up here. And I got to say, understanding the scientific words, it ends up being key to actually understanding a concept. And that's true not just in science. That's true in any area where you're learning. You've got to make sure you understand the vocabulary words and that you can maybe give examples of them or counter examples. Like that's the level that you want to be at if you want to have a deep understanding of any topic. And the same is true for my math classes. I'm a college math professor. I'm teaching these seniors in college, these really smart math students. But if they don't know their definitions, they fall on their face every time. And
I'm going to interrupt you. Science Mom Jody asks, when are the elemental trading cards due? December 1st. So you've got time. You've got time to do them. Yeah. Let's go ahead and reveal this answer. An enzyme is a
is it a
protein that makes an action happen. Good job, you guys. And I also called it a catalyst. Catalyst and enzyme are two words that are often used somewhat interchangeably.
So a catalyst is something that
makes a reaction go faster. And most enzymes are very, very fast.
Like I say, it starts it. Is it? Yeah. Causes like a chain reaction to begin.
Yeah, it causes a reaction to happen.
Like a catalyst. All right.
Next one.
They named it catalase. Like that was lazy.
Yeah, this particular enzyme has a kind of a confusing name. All right, next one.
All right. Question number 4. If a cow lived in a world with no bacteria, it would starve to death. True or false?
Ooh, and maybe we should clarify that this cow is trying to eat grass. Because what if it wasn't eating grass? What if it was eating something else?
Wait. Like, could a cow just eat pancakes? And
you're the one that grew up on a farm. You tell me. Because you grew up with cows.
We didn't offer them a lot of pancakes. Maybe we should have, but no. I'll tell you this much: they liked it a lot when we would pour molasses on the hay. They'd eat the hay and just leave the stuff that wasn't quite as yummy, but then we'd push it back up and pour molasses on it. The cows really like that. So,
did it make the milk taste funny if they ate molasses?
No, I don't think it made a difference to the taste of the milk, but it made them eat more, and the more they would eat, the more milk they would give. Probably they're getting energy from the glucose in the molasses, or the rest of the food.
Probably.
Yeah, okay.
All right, let's finish in reveal.
All right, the chat definitely has picked one answer. They're saying that this is true, that the cow would starve to death in a world with no bacteria.
Cows absolutely need their bacteria because it's the bacteria that makes the enzyme that can digest cellulose. So without their bacteria, they would not be able to digest cellulose, which is amazing, isn't it?
Which is crazy, the idea that you could have a full stomach and it's just not doing you any good.
And if your stomach's full of something you can't digest, then it's not doing you any good.
All right.
So I'm seeing several people saying they've got 4 out of 4 so far. Good job, you guys.
All right, our final question. True or false, human beings can digest cellulose?
Oh, you went easy on them today, Math Dad.
That's okay.
They're totally going to get this one.
Every once in a while, you've got to give them some easier problems.
I know what you're doing because tomorrow is a game show review. So you're saving up all the hard questions for tomorrow. Is that right?
Yeah, well, we'll see. They're going to have to bring their A game if they want to compete. Yeah, this is the minor league stuff. But the game show review, we're playing for real points. But okay. So some people have picked the other answer here.
Yeah. So can we digest cellulose? True or false? We can digest celery. Celery has cellulose. Can we digest celery or can we not?
That's a good question.
Are some of the things we were talking about. Let's go ahead.
The other question is, would you want to?
Do you like celery, Math Dad?
No.
I think celery is good.
I mean, if I were really hungry.
But I like celery best when it has tons of peanut butter on it. In my opinion, the best use for celery is as a vehicle for peanut butter.
Okay, well.
You scoop it in the peanut butter and eat it.
If you're using it as a scoop for other food, a lot of stuff becomes palatable in that case. All right. And the answer here is false. Humans can't digest cellulose. We don't have the enzyme.
We don't have the enzyme that you need to break that bond. So that
only the bacteria did.
Yeah. But that doesn't mean we can't eat cellulose. We eat cellulose all the time because it's a big part of plants. And celery in particular has a lot of cellulose and a lot of water and not much else. So I've seen a lot of little memes about how when you eat celery, you're actually burning calories. There's some truth to that.
Oh, that makes a lot of sense.
I want to show this view of our pan real quick before we go. I know that there was some nervous discussion in the chat about whether or not I was going to knock over this bottle by accident, and I didn't. I kept them.
Well, and the bubbles have actually gone way down from their peak, so they're slowly popping.
They have, but just because it's very satisfying. Watch this, Math Dad.
Jackson Pollock painting here.
Yeah, trace our finger through and look, it's like a marble pattern. Isn't that satisfying?
That is. That's really cute. Now we need more colors of food coloring so we can make better art.
MR Roblox asked, how did the elephant toothpaste not explode? And I should say, because you'll see this experiment online a lot, the one where you see the foam shoot up super high up to the ceiling, that's using 33% hydrogen peroxide, which is quite dangerous.
You can't even get that at the store, right?
No, you can't. And if you spill 33% hydrogen peroxide on your skin, it instantly would bleach it white and burn your skin. It's very reactive. 3% hydrogen peroxide, on the other hand, that you get at the pharmacy, that is quite safe.
Pretty safe.
Because if it's 3% hydrogen peroxide,
it's 97% water in that case?
It is. It's 97% water.
All right.
So it's mostly water.
Well, you still wouldn't want to drink it, but it's not going to harm you.
Yes, it's quite safe. Now, we are just about out of time, you guys, but real quick thing I want to remind you of. Tomorrow we have a game show review. We hope that you will join us to test what you've learned so far in chemistry. And then we have an earth science class that is starting in January. So please check out, we're posting to social media and there's information on our website. If you'd like to join us in January for earth science, please check that out.
So Rachel Rinkins had one question here. She said, Science Mom, if we lose a cell membrane, we would get cancer. I'm not sure if that's entirely accurate, but if a plant loses its cell wall and cell membrane, what are the consequences?
That is a little bit of a tangent we don't quite have time for now because it's 10:45, but plants do also have cell walls made mostly of cellulose, as well as some membranes. It depends on what type of plant species you're looking at.
But without a cell membrane, the cell's going to die, right?
We will talk about this more when we talk about plankton, because next week we're going to be talking about cells, and we'll talk about plankton. We will talk about this then.
Okay, so that was a good lead in to where we're headed.
Yes, we are headed toward biochemistry. Work hard.